There are two types of forces: contact forces and action at a distance forces. Contact forces result when two objects physically touch each other. If the objects don't touch, there's no contact force. Action at a distance forces result even when two interacting objects are not in physical contact. Think about the force of gravity. Do you think a gravitational force is a contact force or an action at a distance force? Gravity is a force that causes two bodies to be attracted to each other, even when the two bodies are not touching. We use the term weight to describe the force between the Earth and an object. It's a gravitational force that acts at a distance. If you were to parachute out of a plane, you wouldn't be touching the Earth, but gravity would be at work, pulling you toward the ground. Examples of a contact force are the force that you apply to a rope when you pull on it. We call these applied contact forces because one object applies a force to another object. A force that resists the constant pull of gravity toward the center of the Earth is considered a contact force. When you sit in a chair, the chair exerts an upward force on you to support your weight. Your weight exerts a force on the surface that supports you, while the surface that supports your weight exerts a contact force on you. A contact force that results when an object rests on a surface is called a normal force and always acts perpendicular to the supporting surface. Friction is a type of contact force that results when two objects come in contact and resist a sliding movement. When you push a box across the floor, a frictional force acts against your pushing force. The rougher the floor surface, the greater the frictional force, at least until you overcome the friction to move the box. Let's look at a situation where all these types of forces act together on a single object. A man tries to pull a donkey with a rope, but the donkey resists, and neither of them moves. We'll concentrate on the forces that influence the donkey. The Earth's gravity acts on the donkey. The ground supports the donkey's weight and exerts a normal upward force on the donkey. The man exerts an applied force on the rope, which is transferred to the donkey through the rope. When the donkey resists the pull of the rope, there's friction between the ground and the donkey as it digs in its hooves. This is called a free body diagram. It represents all of the forces acting on an object. Engineers, mathematicians, and scientists use arrows called vectors to represent forces. The length of the arrow indicates the magnitude or amount of force, and arrowheads show the direction of the force. In this situation, the lengths of the normal force vector and donkey weight vector are equal and point in opposite directions. In other words, the donkey's weight and the normal force are equal in magnitude and opposite in direction. The same is true for the applied force vector and the frictional force vector. These forces are also equal and opposite. If the donkey is stationary, the forces in each pair cancel each other out. Total vertical and total horizontal forces are zero. This means that the donkey is in static equilibrium. It's not moving in any direction. But the donkey is only stationary as long as it doesn't tip over. How can we tell whether this will happen? We need to understand moments of forces to figure out whether an object will tip over. A moment of a force is described as a turning force, and it's caused by a force acting on an object at a point some specific distance from a fixed point. The force tends to rotate the object about the fixed point. You can feel a moment of a force. Hold the end of a ruler as a friend pushes down on the opposite end. When you try to hold the ruler still, you can feel the rotation caused by the force your friend applies, or the moment that results from the force. Consider the moment caused by the weight of a penguin on a diving board. We need to know the magnitude and the direction of the moment to fully describe it. Typically, a moment that causes counterclockwise rotation is positive, and a moment that causes clockwise rotation is negative. We use this convention only to make calculations easier and consistent. Write this formula in your notebook. It says the magnitude of a moment of a force about a point, P, is equal to the force times the perpendicular distance from the point to the force. Let's calculate the moment caused by the penguin's weight at the supported end of the diving board. Call the point at the supported end point P. The penguin weighs 30 pounds and is supported on the diving board at 12 feet from point P. So the moment caused by the penguin's weight is 30 pounds times 12 feet, which means it creates a moment of 360 foot-pounds. This is not an applied moment force. It's just the result of the penguin's weight. The moment is positive because the force turns the board in a counterclockwise direction from point P. What would happen to the magnitude of the moment if the penguin moved closer to the support? Calculate the moment at point P when the penguin is 9 feet from the support. The moment would be 30 pounds times 9 feet, or 270 foot-pounds in a positive direction. Where would the penguin be on the diving board if the moment resulting from the weight at point P is 120 foot-pounds? Substituting 30 pounds for the force and 120 foot-pounds for the moment, the result is 4 feet. So, when the penguin is 4 feet from the support on the diving board, its weight will cause a moment of 120 foot-pounds at point P. In part 2 of the Force and Stability series, we'll use the moments of forces to help us determine whether an object will tip over when we apply a force to it.